All right, so Unit 13, Lesson 2 is about compound interest. Lesson 1 was simple interest, which is a linear function. Compounding interest is an exponential function. So you may remember our exponential format. One of them, at least, was that y equaled 1 plus r, which was your growth rate for a exponentially growing function, raised to the x. Remember that there was an a term out here. So another thing was y equaled a times b raised to the x. And for a growth, b equaled 1 plus r. And this a value right here, I should have an a value there. I didn't put it there before. All right, so this a term would be right there. And that's your starting point. Remember, that was your starting point. And then this was 1 plus your growth with your growth rate. Okay? So let's see how this function works with compounding interest. So the equation starts with the amount at some given time. I don't know why that was so wonky like that. Let me do it like this. So the amount in some given time, that is your y value, okay, equals your a value, which we say is p right here, which is the principal, right? That's your starting point. Okay, so they just put it in financing terms. Okay, plus your growth rate, and your growth rate here is going to be 1 plus your APR, right? Which is we say R. It's hard to type this. Use brackets. 1 plus. Now your interest rate is usually annually. Your annual rate, APR, is an annual rate, and so you have to divide it by the monthly, which is 12. There's 1 year per, or 12 months in 1 year. This is an annually. This is a 3.75 APR, which stands for annual percentage rate. So you got to put that in percent. That's a percentage. So you got to put this into decimal form in this port as part of that, right? And then this whole thing, the whole thing in brackets, is raised to 12. I'll just do it like this. Is raised to 12 times t. Okay, and t is the time. T is our x value here, right? Because it's going to be asking you a number of years. So you actually want to figure out the number of months, right? So this is the number of months. That's the number of months. So that's how you how this equation was put together. Okay, so we're going to model this here. Our a value is the final value at any given time. Okay, equals p, which was our initial principal of $1,500. Let's just get rid of this. $1,500. Okay, and then that's our a value from up here. Okay, this is our a value from up here. Okay, times b, which is 1. Since it's a growth, it'll be a plus sign. Why did it do that? It'll be a plus sign. Plus, and then r is this number in decimal form. So 0.03, that's 3%, 75, and we're going to divide that by 12. It's a tiny number. That's how much it's going to get added every month. Okay, whatever that number is going to increase. So 1 plus whatever this number is multiplied by that. So each month it's going to be a little bit more. Like if my, that's fine. Yeah, so if this, now I have 12 times t, 12 times t. So that gives me my number of years times my number of months, right? So the number of months, because this is a compounded monthly. So every month I'm going to take this number. So let's get that number, whatever that is. Let's see, it's 0.0375 divided by 12. It's 0.003125, right? So this term is 1.003125. So that's like 0.3%. Okay. We're going to increase this by 0.3125% every month times however number of months it's going to be. Okay. That's what this number, that's what, I don't like this, using that. This number here, this number is that, right? So every month, right, I'm going to raise this to the number of months. And I'm going to multiply it by the 1,500, and that'll show me how much it actually is, or 15,000. 15,000. Forgot a zero. 15,000. Man. 15,000. There we go. All right. Yeah. So because of that number, and this is just the number of months, presuming that they give me 10 years. You got to figure out how many months that is, time in years. Okay, so what's the balance after 10 years? Okay, so we're just going to take this thing, which is A equals 1,500, or 15,000, right, times the 1.003125. Then how many months is 10 years? Well, 10 times 12 is 120. So we're going to multiply this number by itself 120 times. So when we do that, put it into the calculator and multiply it by 1,500, we get the value of $21,812.11. Okay, so now it's asking what's the balance account after 15 years. Well, it's the same thing. I do A equals the 1,500. 15,000 times 1.003125. Okay, and then instead of 120 months, it's 15 times 12, which is 180 months. So this is going to be equal to $26,302.74. So this is an example of your money making money for you, right? So you didn't do anything with that amount of money. You just put it in a bank account, and at 3.75% interest, after 15 years, it magically became $26,000. So think about the things that would make this money grow faster, right? You go back to our original equation, that A equaled your principal times 1 plus your APR in decimal form. decimal form divided by 12. That's the number of months, or the number of times it's compounded, because it's compounded monthly, right? All raised to the number of months. Number of months. Okay, so what could make this grow, right? Obviously, the number of months is going to make it grow faster, right? If I have a larger APR, right, it's going to make it grow faster, because a larger number up here will make this entire number bigger. And then when I multiply it by my principal, an initial bigger principal will make it grow faster as well, right? So higher months, right? Higher that, and a higher principal will make that go up. Okay. The biggest factor in here is the percentage, right? A higher percentage rate makes this grow faster. It goes from something like this. That was really bad. It was going pretty good there for a second. Something like this to something like this, right? With a bigger APR. Okay, where this is the money and this is the time. Okay, so there's that one. Okay, and then we can figure out determine when the savings account will reach 30 grand. Well, here's 30 grand. This is 18.15 months, or 18.15 years, right? So that's approximately 18.5 years, right? And again, here, like, if we have a larger interest rate, it would be like that, right? Even bigger interest rate would be like that, right? So kind of gives you an idea how fast it's going to grow. Okay. So here is, they wrote the equation for you, right? A side-by-side evaluate or comparison of simple interest, the linear equation, time, and versus the exponential equation. Okay, so let's figure out how much each one of these would be. Same amount of principal. So that's our p-value. And then this is our, just remember you have to put this in decimal form. This is R. And then T. T is the number of months. Okay. All right. Over here you use T as a time in years. Okay. Over here, it's the number of months times the number of years. So N over here is going to be 12. Okay. So that's the only difference. I mean, you're using exponential, it's compounded monthly, right? So this is how this looks, right? So the amount it's going to be worth equals the principal, which is $100,000, right? Times 1 plus the interest rate of 0.025, 0.0225 times the number of years, times 5 years. Okay, so that's going to be equal to, let's see, 0.00225 is going to be 1.125, so it's going to be 100K. 100K. Let's get rid of that. That's ugly. You know what? I can probably just do it like this. It's going to be 100K, $100,000 times 1 plus 0.0225 times 5 is 0.1125. Right, so that's going to be equal to, come on, it's going to be equal to 100K, $100,000 times 1.1125, and that equals 1.11250 dollars. Right, so you made $11,250 in 5 years. Okay. Well, let's see what happens when I compound it monthly at the same rate. Right, so it's going to be A equals, I just do it like, oh, it's hard to do it like that. I'll see what I can do. Okay, my initial principal of 100K times 1 plus, now this is where it gets a little bit dicey. Okay, 1 plus my interest rate in decimal form, so 0.0225. Divide that by the number of months, because it's compounded monthly. Right, so it's an annual percentage compounded each month. So each month I'm getting 1/12 of that annual compounded interest. Okay, raised to the t, which is 5, times 12, which is 60. Okay, so when I plug all the numbers in here, right, I get A equals $111,895.44. Okay, so which is, a couple $100 more, a little more than $600 more in the 5 years. So compounding is better in that case. So how about 25 years? Let's use the same thing, right? Instead of the 5, I'm going to turn this into 25. So I'm going to get A equals 100,000. I could probably do this linearly easily. So 100,000 times 1 plus 0.0225 times 25. Okay, so that's going to end up being, if I plug and chug of that with the right order of operations, I'm going to get, $156,250. So in 25 years, that money made $56,000 and a little bit more, $250 more. Right? So that's not bad. It's for doing nothing. Okay. But you still have to consider inflation and stuff. But that's an economics class, not a math class. All right. So here it's the same thing, but instead of 120, instead of 60 right here, you gotta do 25 times 12, which is 300. Right. So now my new equation is, when I change that number to 300, right, it comes out to be A equals $175,413.05. Right. When I just change that number to 200, that's what I get. Okay, so you can see that this value is significantly bigger over the long run. You made $75,000 instead of $56,000, and then a few little small difference, right? So that's the power of compounding, right? It grows better than a linear equation will. A linear equation will grow like this, where an exponential equation will grow like this. And then that last year's is where it really starts to take off. Okay, so anyway, I hope that this helped you with this lesson, and we'll move on in the unit.